Now we'll introduce our first speaker, Dr. Noreen Hynes. She is coming to us from Hopkins University, and she will have a very engaging presentation for us with a different aspect of science and medicine that I'm sure you have never thought about before.
Okay. Many of you saw me in my mask, and so people often say, why are you still masking? And so my answer is, if I get COVID, I can't see patients. And I'm a specialist, so guess what? Then they'd all get called, and sorry, not a good idea, you know? So that's the reason. So are you going to, do I have to press something here? I'm sometimes challenged in this respect. Okay, so I had to think to myself, I'm coming to see a whole bunch of mostly high school, but some middle school teachers. I do want you to know that it was high school and middle school teachers who actually were inspirational in helping me decide where I was going to go. My chemistry teachers, Mrs. Calmaneri and Mrs. Gross, my biology teacher, Mr. Thompson, and cutting up crayfish and whatnot, and even my physics teacher, Mr. Kaplan. So they all made a very big difference in believing, yeah, you could do something like this from this blue-collar kid, you know, from New Jersey. So what I want to talk to you about today, I should talk about things I know about, but things that could be potentially relevant when you go and talk with your students. And so I'm going to make a case today that medical countermeasures, that I'll give you a real definition of that, it's all about STEM. And it's not just biology or microbiology, it deals with chemistry, physics, engineering. You have a lot of people who are data-driven. We're getting into AI now, which is so big, AI in medicine, etc. So there's a smorgasbord for students. So I just want you to know, influencers are hot stuff these days. I think that you guys don't realize you are all influencers. Okay, every single one of you is. So not the 15-year-old, yes they are too, but what I'm saying is you have great impact on the future generation. And also, when you're talking to your students, it's worth saying to them they should read the book, maybe they don't want to read, maybe they want to listen to an audiobook, called The 100-Year Life, okay? Because they're going to live a lot longer. A child born today, on average, will live to be at least 105, over 50%. So doing the exact same thing, doing it the way we did it at the turn of this century, or even the turn of last century, isn't going to work for the future. Okay, so having a diverse type of things you can do throughout all of STEM if you want, or even not in STEM. So, for instance, looking at what the most in demand, according to Teen Life, okay, I thought that was sort of a good reference, these are the most in demand STEM type careers at the moment. And I can make a case to you that, think about this, there's not a single one that isn't potentially in medicine and public health, but in many other places as well. You can't be an epidemiologist without understanding data. You can't get ready to model what's going to, what could be in the future, including the outbreak of measles now in Florida, what's going to happen when you don't immunize your kids, mechanical engineering. People don't think that it's very important to make an inhaler for someone who's asthmatic, or to deliver a nebulized product to someone who's wheezing, requires someone understand the physics and mechanics of small particles and where they can go down into the lungs. So there are many, many things that a student could get excited about other than seeing blood, doing surgery, or growing a bug in a petri dish. So what I hope today to do with you is to show you that there is a critical need for STEM people in all of these areas that deal with medical countermeasures. The discovery at the bench, The formulation, you know, think about it. A pill is not just what the active ingredient is, it's how you put the pill together. And those formulations have a lot to do with chemistry and biochemistry, not with biology, okay? Testing, manufacturing, how to deliver it. Okay, if you have a great idea but you can't get it into the arm or the mouth, guess what? You have a problem, okay? So it really is difficult if you have to go all the way into a small village somewhere, or even here in the United States in the Mississippi Delta. You have issues if you have to carry something in and deliver it through a needle in the arm. So what's an alternative? Can you do a patch? Can you do something that can tolerate ambient temperature? These are things that we need desperately, and we need them better than we have now. And that's students of today in high school and entering college will be the people that make the difference in the future. And so we need to make them excited to get into this. So I sort of started with the whole idea that I was going to talk about these things, medical countermeasures. Well, what are they? They're things that help protect, prevent, treat, and diagnose. So it's vaccines, biologics, treatments, and diagnostic tests, okay? And not just for biologic stuff, it can be radiologic, chemical, the whole 9 yards, and of course, emerging infectious diseases, which we all so closely have been experiencing in the past several years, okay? And it's biological products, drugs, devices, all the things I talk about. All of these things do not require someone who is, and actually, if you just left it to someone who, like me, is an infectious disease physician, I wouldn't necessarily be very successful in how do you make a good personal protective equipment. I could say what I want. I don't want to get exposed, but I wouldn't necessarily know how to do it. So right now we're planning some research with the Applied Physics Lab, which is one arm of Johns Hopkins, and we're looking at how they can help create sensors that we would put on our personnel who take care of people, potentially high consequence pathogens. So we'll know when to remove them, when they're under too much stress. That is not something that I would know how to do, okay? But I can work with these really terrifically smart physicists, which quite a few of them are, and engineers. So I wanted to give you some sense that, you know, you've heard people say, well, why is it taking so long? Why is it taking forever to get a product? I want you to see something here. People forget, it starts with basic research. Do I have a little? There. It starts with basic research. And of course, you're doing lots and lots here. Then you think you have a drug. Then preclinical. That's on the bench. You're going to grow something in a petri dish. You're going to do something like that. You're going to put it in small animals to see if it works. And then, you see, we're getting thinner and thinner and thinner. There's a lot of work that gets you to an FDA-approved medicine, vaccine, etc. Okay, so how long does it take? On average, okay, you're going to say, well, it takes you about a year or so, because that's how long it took us to get those vaccines out, right? Sorry, usually it's 12 to 16 years, okay? It's a long time. Remember, it makes a difference whether it is a product that's going to treat someone, and the severer the thing you're going to treat, the more side effects you will tolerate from the drug. But that's not true for a vaccine, okay? If you're going to prevent something, why do you want to give me something from a vaccine? So those clinical trials, as you're going to see, require lots more people than a drug necessarily. So there are all these phases that you hear about. IND means it's an investigational new drug, IND. And that can apply to vaccines as well as to drugs themselves. Phase 1 just means that you put it in the animals in preclinical, and now you're going to put it in the first person. First thing you want to do is find out if it's safe, okay? So you think, what are all the STEM things you could do there? Yes, there's someone who needs to be able to put it in, but you need someone who understands data. How many people do you need? We need the biostatisticians. We need lots of people and laboratorians, et cetera, who can help do this. And in every clinical trial, you will need to have some sort of test on the humans, if it's a pharmacokinetic test or an antibody test, and often those have to be created de novo, okay? So that often takes a molecular biologist, an immunologist, and different scientific backgrounds that are necessary. So it can be very exciting. See, you don't have to be someone who has to see the blood and guts. So I just wanted to give you this is that standard pathway. Sometimes you can get around that pathway, as we're going to show you, but you can see it takes a long time. It can take maybe 16, 17 years. And that's provided people really want what it is, and there's a demand for it. Think about that. If very few people get something, and the only people who get it are people who live in low and low middle income countries, I can assure you, people are not interested. Why? Someone has to make it. And what's the important thing for a commercial entity? It's return on investment, okay? So, these are the things that get in the way. So science often chooses the low-hanging fruit. You look at something, we already have a lot of data, this looks like it could work, I don't have to make it that 16-year timeline, I can make it shorter. Economics, there you go, math, lots of math. And there are people who will tell you this isn't worth it to do because the return on investment is too bad, okay? And then regulatory. People don't think of regulation. FDA is now called regulatory science. And the reason is, I don't think anyone understands the type of scientists that work at the FDA. They might be clinical trial specialists, basic scientists, bench scientists, at various centers in the FDA, they still do bench research because they want to make sure that what manufacturers are doing works. So, I mean, there's a lot of opportunities for someone who is science, math, engineering based. So, a question that comes up very often is, you hear, well, it's a randomized, placebo-controlled trial. So that means you're going to give the active reagent and something that looks like the active reagent but isn't, okay? So would that always be an ethical thing to do? Now let's see. I have here in this vial Ebola virus. And I have a control over here, a placebo. Let's see. Am I going to give someone a drug and then test them? I don't think that's exactly, we would not consider that, how do I say this? That's not ethical. However, when we were hit with brand new SARS-CoV-2, we had never seen this before. People are dropping like flies, either from illness or, if you remember how many people went into hospital initially, the virus wasn't exactly the same as it is now, trust me. Having run that very first clinical trial that was going on here in the United States, we were one of the international sites for the drug called remdesivir that you read about, and I was the site principal investigator for that. And so we did in fact have a control, because we didn't know what worked, okay? So we had an active reagent and something that looked just like it to figure out was it going to work. And I'll talk about it a little bit more. But there was no good answer about how you were going to do this and how you would do it in a way to get the answer originally. We just didn't have, why not? There was minimal research done, but then 9/11 happened, and suddenly everyone thought, you know, we had been thinking about this for a while. Is there something else we can do to get us the answer that we need in a way that's ethical? And then, this is a STEM application par excellence. This is the animal efficacy rule. Okay, this was first put into allowable since 1999, but the regulators and the regulatory lawyers and whatnot really didn't get around to putting it to use until Congress told them they had to after 9/11. And so it's a regulatory pathway that allow to get drugs and biologics, et cetera, approved when it would not be ethical to do an efficacy study with humans. And you go, oh, so how come you can put it in a human? So there's a lot of things that go on in the animal efficacy rule. So if, let's say, you think you have something that could work and you've worked on it on the bench and you have it in small animals, look for a small animal that reacts to whatever the pathogen is, for example, very similar to humans. And then you expose them to it. Pretty cool, you know? Except if you love animals so much and you never want testing in animals, and then this does become a challenge. And then after you do that, then you go to those safety, that first phase 1, and you put it in some humans to see at least if it's safe, and then do they appear to have a reaction to it in terms of what happens in their blood tests, et cetera, that are similar to what happened in the animals. Okay, and if you get enough of these data, then, particularly if you're using large animals like non-human primates, if they have a similar reaction to humans for whatever it is you're testing, actually the FDA in certain instances will allow you to register the product and actually license it. So they both a regular trial and therapeutics, if you're going to use this, they both have to have small animal studies. The biologics and drug treatments, you're looking for efficacy in animals, you look for safety in humans, and then you look at these pharmacokinetics. What's the uptake? How does it burn off? Does it look like it happened in animals? But for vaccines, you have to ask yourself, okay, you look at what was their antibody or immune response, but then you have to say, what correlates with protection? Modeling, I see math again in my mind here. So what are the correlates of protection? It took them a while to figure out how they would do this. So what are the immune parameters? So I thought it was very important to bring up to you this whole concept of all immunity from let's say a vaccine is not alike. And unfortunately, you have a lot of people who say, I got that vaccine and I still got it. Okay, I still got it. I got the flu vaccine. I don't get the flu vaccine because I get the flu after I get the flu vaccine. Okay, these are all inactivated vaccines, but the expectation, unfortunate for many people, is that if they take a vaccine, it will give you what's called sterilizing immunity. If you get the vaccine, you will never get after you make your immune response. And there are some vaccines that's true for, in most cases. So for instance, children all now get hepatitis A vaccine. Chances are, unless they're swimming in blood or a product that's food that's full of hepatitis A, or get a blood transfusion from someone who already has hepatitis A swimming around their blood, they're not going to get hepatitis A. They have sterilizing immunity. Then you have other people who are protected against symptomatic disease, but in fact they still could become infected. And probably a good example of this is yellow fever vaccine. Now, yellow fever is a live vaccine, hepatitis A isn't. And we used to say you got it every 10 years, but now we say it's good for life. It's good for life because you have protection against symptomatic disease. You could still get infected and you'll raise your antibody up higher, but the mosquito you won't have enough virus swimming around for the mosquito to pick up the virus and then give it to others. So you give that particular vaccine to protect people, but to protect populations so that mosquitoes don't get them. And then there's protection against severe disease. And so this is what people have a hard time with. That's a very good example is influenza. Is the one that really you need to think about, because influenza in the extremes of life kills. It has high hospitalization and fatality. That is the thing with the COVID vaccine. Okay, you do if you take it, and you're younger, you are less likely to become sick, that's true. Where you still haven't gotten to the point where we're sure that if you're exposed, you can be asymptomatic and you can still shed virus like anything and make other people sick. But it keeps you from being ill, keeps you from probably transmitting to some other people, etc. But when you think about it, you want people at the extremes of age, your grandmother, your grandfather, and your small children, particularly under the age of 1 and 2, to survive, okay? And people don't realize, I bet most people in this room don't realize, you know, this particular coronavirus that we have lots of other coronaviruses. 30% of all common colds are actually coronaviruses. But what people don't realize is that people at the extremes of age, young children in their first year of life, and older people still die of the common cold virus. Okay? And not at low rates, in nursing homes, etc. This still goes on. Okay? So I think that people don't understand that there are lots of non-absolutes that exist. Okay? So to me, if I could make this message something that somehow you could put into your modules of instruction, to have debates or something amongst your students on what this means, I think it would be terrific, because they'd have to go do a data dive, find out what the reality is. So, but here's something, but not all vaccines have a correlate of protection that we can use. They only have surrogates of protection, and in this case it could just be neutralizing antibody. So we know that for some things, if neutralizing antibody gets to this, usually someone doesn't get sick. So they see whether or not the vaccine will get it up to that level. And I'll give you a demonstration of one of the vaccines that we did that with. And I think smallpox, whoever hears of smallpox anymore, you know, it's eradicated. So it's not a big anything. And now you would only see smallpox if someone released it deliberately or technically accidentally. There are only 2 places in the world that are supposed to hold the virus. That's the vector lab in the Russian Federation and the CDC. That's it. And it requires high-level biocontainment to handle. And so we did have a vaccine here in the United States called Dryvax that Wyeth made. And there's some people here who maybe got a smallpox vaccination as a child, and someone like me who worked overseas in places that had smallpox before it was fully eradicated, that got more than one in their life. But there wasn't much Dryvax, you know, and after 9/11, everyone went, what's the next thing? And the letter attacks with anthrax, everyone went, we need more, we need more. And so this was a very interesting development that required a lot of science and a lot of engineers and a lot of everything. This really brilliant guy, Tom Monath, a physician scientist who had worked at CDC, worked in the Army, and had created a company, a Canvas, to help answer this question, took the original Dryvax vaccine, a live attenuated vaccine, grew it up, and I want to make clear to people, the smallpox vaccine is not smallpox virus. It never has been. It's called vaccinia virus, this gamish that we think maybe comes from horse, cow, a mix of horse, cows, etc. But it works, okay, against this class of viruses called orthopox viruses. And so he went and grew it up, and he took a look at what these plaques looked like, these growth islands, and picked them up, picked, and then tested them in animals to see what the effects were in animals. And then he did safety trials in humans to see how much they needed, concentration, and then what was the correlate of protection. So you could give the dry vax to people and see what antibody level they got. Then you could take the new vaccine that they were creating and see if it was equivalent, okay? So in this case, you had something you knew worked, okay, which was the dry vax, and then you had the new vaccine, and this was licensed, weirdly, only for smallpox, not for anything else, even though the original license, the package insert for dry vax said for all orthopox viruses, but single dose vaccine, and after ACAM was licensed, WISE said, thanks very much, we're not going to carry the license anymore. So there is still some of this in the strategic national stockpile, but the dominant smallpox vaccine is ACAM 2000, and there are probably enough doses for everyone in the United States. Additional, and then some. And additional studies have shown you can even dilute it, and you can get even more doses. What's the duration of efficacy? Who knows? Used to be you had to get it every 3 years if you were going into a place. Why? Because who knows, you know? And they still do that for people who work with orthopox viruses. They still have to get the vaccine every 3 years. But then there's another vaccine. Now this has been around since 1931. That's when it was first licensed by the FDA, the dry vax. But then we have modified Vaccinia Ankara. This comes from Ankara, Turkey. And it was modified and modified and modified and modified. It lost a whole lot of genes. It became less virulent because anyone who's had a smallpox vaccine, the original one, knows your arm can get really yucky and you can get sick and run a fever and get big lymph nodes under your arm. So this one was a different pathway they used several things. Remember, the smallpox virus, the vaccines are good against orthopox viruses. So that smallpox, we're now calling it mpox. We used to call it monkeypox, but it's still monkeypox virus because it was found in a monkey. And it's live, but it doesn't replicate. So you can imagine that's very nice because replicating live vaccines can't be given to immunocompromised persons. And certainly the smallpox vaccine, because it gives you can't be given to people with certain skin conditions either, like eczema. So this has a long history. As a matter of fact, if smallpox hadn't been eradicated, this would have become the licensed vaccine for use in Germany and probably the Netherlands, because they had lots of data. So ultimately, FDA has actually been around for quite some time. But of course, FDA wanted more stuff. So for the animal rule, they used several things. The animal rule, but they used monkeypox virus as the challenge virus. And then there were a few studies done in small animals at CDC with actual live smallpox virus. And then in countries, in Central Africa and West Africa, who actually had monkeypox endemically, they gave the vaccine, but in sort of a, not exactly a blinded trial, but they'd give it to some people and not to others. And some people wanted and others didn't. And then they'd look at who got monkeypox and who didn't. And then they looked at the neutralizing equivalent now with ACAM. Did you make enough antibody to look like you were going to protect it? So ACAM was equivalence because it looked like you got the same antibody as dry vax. So it was all, and what's the duration? Who knows? Maybe 2 years. So, and this was licensed to protect against two things: smallpox and mpox. And, but it required 2 doses. But maybe not. So the only reason I bring it up because mpox you've heard a lot about these days, okay? So the approved therapeutics, the treatments that we have for smallpox, toxicity studies were done, safety trials, where they're going to be safe, PK, that's the pharmacokinetics, very important in a drug. How long does it take you to get as high as you need to go, and how low does it go, and how fast? The challenge virus, again, was not smallpox virus, it was mpox virus, because it was close enough. There were no animal and no human efficacy trials for this as a therapeutic was done with mpox disease. And it was approved, unfortunately, these all were only approved for smallpox, although we used as a challenge virus monkeypox. Okay, I'm not the FDA, I didn't make that rule. So these are all the things that we have that were all approved under the animal rule. The very top one is for anthrax. I gave an example. Everything else is for smallpox at various ages. So we do have several antivirals in the strategic national stockpile. And you probably have heard in the newspaper about TPOXX or tecovirimat, not because of smallpox, but because of mpox. So to bring up some very important things that you would want to know about. What if it's an emerging infectious disease like COVID, or it's a biothreat? Someone deliberately lets loose something such as smallpox. So you still need preclinical studies. You still have to have clinical trials of some sort. Smallpox was eradicated, so now we consider only a biothreat agent. And then all of our drugs were under the animal rule, and one of 3 of our vaccines was under the animal rule, all 3 approved. But then we have Ebola. Now here's a very interesting, different thing you can do. We learn, okay? And it's a high consequence pathogen to be sure, but it has biothreat agent potential. Not that I ever want anyone to grow up Ebola and spray it around, not a great thing, okay? But, you know, CDC and others worry about this. It's considered a category A agent of bioterrorism. We have 2 drugs, FDA-approved drugs that can treat Ebola Zaire. There are 6 types of Ebola, and so all the same medical countermeasures don't work. And we have a vaccine approved. And look what it says. There was a human clinical trial. Wait a minute. How could there be a human clinical trial? You told me it could be unethical. Most interesting. But let me stop for a hiccup here, because you have probably seen this in the newspaper a few times, this public health emergency of international concern. Now, because there's a PH here, you would have a tendency to want to call it a fake. But considering it's a PHIC, not a fake, okay? Because people would say, oh, it's not real, okay? So there have been several public health emergencies of international concern. These are when the WHO makes a determination that there's something extraordinary happening that could constitute a public health risk and could have international spread and continue to be propagated. And so it very well helps to focus international attention and really helps national governments make a decision about how they're going to launch their emergency strategies on this level. So the different colors show, you can see over here, believe it or not, that swine flu that occurred back in 2008. That was because no one knew what was going to happen with it. It was a combination of 4 different viruses. And then here we go, the Ebola in West Africa. We're going to talk a little bit about that one. It was for a period of time. And then we have mpox and COVID-19 and Ebola Kivu. I want you to notice this one. This is polio. It's still ongoing. This is vaccine-derived polio. We don't use live vaccine anymore in the United States because there were more side effects than we needed and potential deaths, so we only use the inactivated one. But it's much easier to give oral polio vaccine, and there are some in here who have gotten both in their childhood. And so what's happened with the virus in some countries, it's reverted. The vaccine-derived polio is now reverted and is now paralytic again. So that's an issue. We were hoping to eradicate polio, but it's probably not going to happen. So there were things that happened regarding Ebola. So I want to come back to the story of how did this wind up as a human clinical trial? How did we do that? Okay, so in 2014, the West African Ebola outbreak that many of us recall was declared a PHIC. Okay, so there were lots of WHO top-tier consultants, and they did an unprecedented thing. they said, we're going to squish phase 1, because we already had vaccines in development. The US Army and others had been working on it, but they never got any further. You know, they had done challenge studies in animals, but who wants to make it? What's the return on investment? Who's going to pay for it? Okay, so all the way to phase 3, there was a concurrent phase 2, and no one had ever done this. There was a consultation of the smart people, people who could model, mathematics, could look at this. So this is what happened. As you can see, this is not 16 years. We already had the preclinical stuff done. So now we needed to do those clinical trials that could take 7 to 10 years, as you remember, once you get to phase 1. So what they did phase 1, some phase 1s, and then put some phase 1 and 2 together, where there's more people, and then ran them together, and then you could do a emergency use, but then we're going to, wait a minute, phase 2, that means phase 1's only not doing a placebo and challenging, so what did you do here? So believe what they did was the following. The example is the Ebola ça suffit in French. It's enough. This was the only country that still had enough Ebola ongoing to actually do this trial in the way that was done. We knew the incubation of Ebola, because we had enough information on Ebola, was up to 21 days. So what they did was they picked clusters, and they immunized one cluster, and the other cluster they went back to, so you would say, are you going to be a receive it now, or are you going to be a receive it later, okay? But not later than the incubation period, okay? So what they were able to show was that people who got the vaccine within 6 days of a known exposure did not get infected, okay? Did not get infected. And we did not know that. And guess what? This worked. And then WHO said, okay, no one wants to make this vaccine. We will give you $5 million if you make the vaccine and make enough that we could use it in these outbreaks. And the winner was, and our vaccine efficacy, see, no Ebola cases have occurred 10 days or more after randomization in the immediate group versus 16 cases in the clusters of the delayed groups. $5 million if you make the vaccine and get it licensed, and guess what? Merck won. So now there is, and they had to do it within 5 years. That's $5 million to make 5 million doses and get it approved. They did it. Okay, so yeah.
That's a good question. $5 million doesn't seem like that much money. Why did that make a difference to?
That's a great question. Why would $5 million? Remember, all the background stuff has already been done. This was to take it through its regulatory pathway. Okay, this company already had vaccine. This is a manufacturer that knows how to make vaccine. So to make 5 million doses in a good manufacturing practice that met all the requirements was in a vaccine company that traditionally prided itself on its public health commitment to prevention, was in keeping with their corporate ethos. And so, but it's not like it's being made all the time. The U.S. Strategic National Stockpile has some, and then of course WHO holds some for all the outbreaks that keep coming out of Ebola, but it has to be Ebola Zaire because that's the type of vaccine this is. What you should know is it is licensed here in the United States, but I cannot get it because it's held by the Strategic National Stockpile. There's not enough of it. Enough of it is not commercially available here. So if I have someone who's going into the heart of an outbreak, I have to negotiate with CDC to give me some, okay? And it's usually, no, they can get it in country. That's usually what's said. So, very cool. But then we have this other thing, and everyone's heard this. God, Emergency use authorization. Good God Almighty, what is that? And why in God's name do we have it? You know, we've been using emergency use authorizations actually since the mid-2000s, but people just never heard about it. You heard about it for COVID. You know, even when we had that big influenza in 2008, we had it because children couldn't get one of the antivirals. They weren't approved for it, so they had an emergency use authorization. So what is it? You use it when there is no adequate, okay, approved and available alternative. It doesn't mean that you don't have any data. It just means that you don't have the full complement of data that would have gotten it across the regulatory finish line. And if you have nothing else, it can be offered. Okay, so it's it came into being in the Project BioShield Act of 2004, okay? So I'm not going to stop on this, I just want you to know there's a big process, okay? DOD can get its own EUA just for the military, and they sometimes need to do that, and one of the first vaccine EUAs was given to the military for anthrax vaccine. The DHS secretary can chime in, the HHS secretary can chime in, and then ultimately the commissioner of the FDA. So just to remind you, the only one on all of these, okay, in December 2019, if you take a look at SARS-CoV, people don't realize it was in a posting that I first saw in December. The first case was actually in November, and 31 December, the Wuhan Municipal Commission said they had this big viral pneumonia outbreak. I just want everyone to know that this happened around the time of the Chinese Lunar New Year, okay? And Lunar New Year is celebrated not just by Chinese, but by Koreans, by a whole bunch of other people, and there are over 1 billion people who go someplace, either in the country or leave the country. Do you know where one of the biggest outbreaks was early on when this got out? It was not here in the United States, it was in Zambia, because there were over 1 million Chinese working in Zambia who had gone for their holiday and come back, and guess what? I have a colleague who has a research project there. He got severe COVID while he was there, didn't know what the hell it was. Okay, so we knew quickly that it was a beta coronavirus in the same group as the other SARS that some of you might remember that, occurred, and we had some in Canada, we had some in Singapore, nosocomially transmitted, that is cross-infection in hospitals, but it never got out, okay? So there was never a PHIC declared or anything like that. But it had 79% nucleotide homology with the earlier SARS-CoV virus. You remember that was in civets in 2003, okay? And it was named, got the 2 because it was similar. Okay, I just want you to recall that on February 20th, okay, just a month, 6 weeks after this thing came out of the bag, the case fatality rate was noted to be 2.4%, and these were all the cases that there were. And here we are down in the United States, we had 13 cases. That was it. Okay, so here, look at all this this to me is the formula for a STEM teacher to love. I can put every STEM profession in this, okay? Reproductive number, how I'm infected with SARS-CoV-2, how many people do I onward infect, okay? So this tells you, on average, how infectious is a person. But you have to know a lot of things. How long does the infection last? How many contacts does a person have? And how transmissible is it, okay? The most infectious thing that we know of is measles. Oh, I should tell you, everyone's going to get a copy of these slides, okay? And what about inanimate surfaces. Do you remember? Everyone was taking and cleaning their nail because we didn't know, okay? We didn't know because we do know other viruses. For instance, hepatitis B virus. Everyone gets this as a childhood vaccine now. We don't think about it. People forget hepatitis B virus can live on surfaces for 8 or 9 days. Think about that. So we didn't know. And when you don't know, you do things to try to protect yourself. Well, what about those super spreaders? Remember the singers in the church? And all of the cases after that? What's the numerical risk for a traveler? I get on a plane, am I going to get it? I get on a train, am I going to get it? You have to know about ventilation systems, engineering. So, implications of respiratory tract infection if you're asymptomatic, we still don't really have a good handle on that one. What's the true spectrum of clinical disease? We don't know this. You know, we think now, getting smarter, a little bit, slow by slow, we think there are some people who will never get infected. It's probably genetic and it has to do with their immune system. Okay? And we know because there are people who are exposed, we know they're exposed, they're taking care of their kids, their husband, their wives, and they're all sick and they're spitting all over and they're not wearing a mask and they never test positive, not by PCR, not by anything. So there must be something about them. And we do know that there are other diseases that these types of things happen to. So for instance, there are certain receptors that if you don't have, you're not as susceptible to things like HIV. So, and what about, are there meaningful genetic mutations, okay, in humans? Also, we have to learn about the change in the virus over time. It keeps changing. It is not the same virus as it was when it came out when we first saw it. It probably, right now, might be a little less virulent than the original virus. So we learned a lot of things early on. We learned pretty early on that it looked like you had a viral phase when you could actually culture the virus, but then you had this response phase, okay? So here you need a lot of immunologists. And then you had to make all these things. Okay, there are non-pharmaceutical things we all heard about, social distancing, face masks, eye shields. We weren't very good, I have to say, we weren't very good at telling anyone about any of these things as we got the data. Okay, face masks. Wearing face masks does not ensure that you will not get infected. Even me, who would wear what's called a PAPR, you know, I look like I'm in a moon suit when I go in to see if infected patients in the hospital wanted to be in that clinical trial, looking at remdesivir. Technically, I could have become infected. It's much harder. So the mask that I wear should screen out 94 to 98%, but nothing's 100%. So those surgical masks are only 65%. So if people think it's 100%, it's not. Nothing's 100%. Okay, same thing with eye shields. What about treatment? Supplemental oxygen definitely helps some people. Proning. What the heck is proning? Think about this. If you think of your lungs, you have your lungs, you've seen pictures, lungs, and then remember in the back, you have a lot more of that hanging in the back. So the assumption was, I'll just flip them and we'll let them lay on their stomach so that and guess what? In some people it works. Because it works for other diseases. So they actually expand more and get more air in. So it's actually very interesting. And mechanical ventilation. And then these are all the things if you want to treat. Post-exposure prophylaxis, a vaccine, antivirals, and anti-inflammatories. All of these we have been looking at since this came out of the bag. And as you can see, all of them have something to do with STEM. How much? How do you formulate it? How do you make it right? How big is the clinical trial you need? So our clinical understanding has been increasing, but it's still growing. And how do I know that? Every day I see it. So, but where we started, okay? We started with, are you trying me? I have to shut up now?
I'm not saying that exactly.
Okay.
But just about 2-3 more minutes.
Okay. Okay. So, how to find a proven treatment? We had people dying. We had hospitals full. What was the number one Now, everyone wasn't dying. We saw it early on, it was only 2.4%, but by the way they were filling hospitals, we had no more beds. So getting something that would decrease someone's duration of hospitalization became key, okay? So you look for the low-hanging fruit, something you have some information on, and you go for it. So we studied antivirals and treatments first. We could worry about prevention with a vaccine later. We needed to get people moving. So this is what we had in from early 2020 through 2021. These are how many trials we had looking at antivirals. And the remdesivir I mentioned to you is the one that we began with, and it actually was the first to get an EUA, an emergency use authorization, and also the first to be fully approved by the FDA. Why? Because it decreased hospitalizations by 5 days. You go, so what the heck? Think about it at the time. We had no beds, okay? And interesting, you've heard about monoclonal antibodies and everything that have come out since that don't work anymore because the virus keeps changing. This still works, okay? So I won't go into the regulatory pathway, but I'll tell you this, these are all the studies still ongoing, okay, for COVID, because there's so many questions that have to do with drugs, vaccines, diagnostic tests. So just remind you that a vaccine clinical trial, a VCT, is not a therapeutic trial. You need a lot more people if you're going to prevent, because it's safety. People, if you're dying of cancer and they have a drug that potentially could cure your cancer but made you feel like crap for quite some time, guess what? You would take it and it will get approved by the FDA. But that wouldn't happen. That same level would not occur with something to prevent illness or disease. So these are all the things that have been approved. You all have seen the vaccines, the treatments, the remdesivir, baricitinib. And anyone here taken Paxlovid yet? That wonderful metallic taste? But it works, okay? But the monoclonal antibodies don't work anymore, so that's what we have. And just to show you, these are, think about the sheer, and this is an underestimate because all of those over-the-counter tests. Mpox also is an issue. I think I talked too much and they're unhappy with me, so I have to go through this quickly. Just so you know, Mpox has just existed for years and years and years in sub-Saharan Africa, but it came out of the box when it became a sexually associated disease that was transmitted at European raids, as they're called. Again, the same equation applies for everything. And we had only the Bavarian Nordic product was actually licensed for Mpox. Everything else had to be given as an investigational drug because they were only licensed or approved for smallpox. So I want you to know this was a horror for clinicians because they didn't issue an EUA, they did it under what's called an emergency IND, an 8-page consent form for every single person you wanted to give TPOXX to. God, it was horrible. And it is horrible because you still have to do that. So we do have therapeutics, we do have things, we have diagnostic tests that are under emergency use authorization. Yes, I didn't mention those much, but they're there too. And so I hope that I was able to, in this speed talk, inspire you a little bit to think you could talk to your students about, they all don't have to become doctors. That is not the be-all and end-all. There are so many wonderful things. Not only that, if a 100-year life is true, they can have many different careers, okay? So, just remember, you are all influencers, and I am much more than me, and I think you are the inspirational people who will be making a difference in the lives of your students who go on to make a big difference in the world because of you. That's it. Thanks. And no time for questions, right? Do they have a breakdown?
Do we have any questions?
Yes, sir.
Yeah, the time between pandemics, it used to be like a century between major ones. They're saying that that period is going to be shorter.
Well, yes and no. You know, I like to be evidence-based. So the reality is, we have better surveillance systems now in all parts of the world than we did, although the surveillance systems in certain areas are much better than others. Additionally, our diagnostic capabilities are better. So the fact that people got a high fever and died is they got a high fever and died, but now we can find out, more likely to say why, and did everyone look the same? Okay, so the other issue that is on the table, I don't want to be hit by lightning. There probably is something in climate change. It is making a difference. Also, the way we live, we're bringing more people into cities. There's mega cities now, and people have moved around the world from more rural settings. And once you put lots of people in places, it's much easier to propagate things that are transmitted person to person, but also even to have contaminated food and water that could wind up causing outbreaks, and some of those things that can then be propagated person to person. So it is possible, yes. And like, for instance, there is a flavivirus like dengue, you've heard of dengue, St. Louis encephalitis, and there's another one that's not mosquito-borne like the others, but actually tick-borne, connoisseur forest virus in India. There's a huge outbreak right now in Karnataka, and they haven't seen a large outbreak like that in years and years and years. So why? Climate. Okay, was there another question? Yes, sir.
I was wondering if the database of the Human Genome Project has had any effect on how clinical trials are done, if there's any strategic analysis about who's given the I guess, clinical trials to, or how that's done.
As a matter of fact, your question is a good one. Who is enrolled in clinical trials? And is there in fact bias? Okay. We recently have written a paper and talks about whether or not this ACT trial that we did, there were 4 segments to it, whether or not it was discriminatory. And the fact of the matter is, you have to look at whether or not it is or isn't. It appeared not to be. But the fact of the matter is, you need to think of something like in Baltimore City, where I work. Children in the inner city, and I used to hear a program in some clinics in the inner city, an HIV STD program at 2 huge inner city clinics, and I would hear parents say, when their kids were in the clinic with them, if you don't behave yourself, I'm taking you up the hill to Hopkins and letting them experiment on you. Okay, so, no, I mean, I want you to know this is embedded into the culture. Not to mention, when you know things like the government allowed people to continue, usually black men, to continue with syphilis, to see their natural history, even after we had penicillin and we knew it could be treated. Okay, so there is a lot of suspicion. So when you run a clinical trial, it is incumbent upon you to have community advocates who want to work with you with people who are marginalized patients. So when we participated in, when our Center for Immunization Research participated in COVID-19 vaccine clinical trials, we didn't even attempt to do that without community advocates who worked with us to ensure that there was the right, it was representative of Baltimore, which is a 70% African-American city, has more and more and more Latinx people, and to make sure that all were included. You know, so you have to work at it. So yes, it's an issue, to be sure. Any other questions? Okay, thank you.